So is my screen visible to you?
Yes, skin is
No.
visible.
Okay. So let me welcome you to the week 5 live session of Quantum Chemistry of Atoms and Molecules live session. Actually, the last class I had to postpone and I did it in on Saturday. We did on Saturday and recorded and uploaded the session on YouTube. I hope you have gone through it. So the previous day, what we have done is that we have discussed a little. We have obviously solved a few numerical problems on particle in a box and those kind of 2D box also. And then my plan was to discuss a little bit of that algebraic method, raising operator and lowering operator in harmonic oscillator problem. And then actually we have solved a few assignment problems which was there for assignment 3. And have you gone through it? Did you have any, do you have any doubt regarding those harmonic oscillators lectures? Uh, Particularly, suppose in terms of understanding lowering or raising operators.
Yes,
Do you have?
I have seen the lecture.
So I am asking that if you have any, do you have any particular doubts in that about the raising or lowering operator? Today's plan actually I had couple of not couple of means a few questions
The
on
thing,
yes. I'm hearing. Can you repeat please? Okay. So actually, today my plan is to. So I have collected a few more questions from this solvable system like particle in a box and harmonic oscillators, and from Macquarie's physical chemistry book. So these numerical problems also would help to means if we solve it together, then I hope it would be good for understanding as well as solving problems in the exams also. So today actually particularly we're not starting with rigid rotor theory and numerical problems. Maybe we can the assignment problems maybe we can do in the next week. So today I have a few questions on this. Like, so the first question, suppose this is from a Macquarie Simon book. So what the question says is that uh, in section 3.5 we have applied equation for particle in a box to the pi electrons in the butadiene. So actually this question is related to the that spectroscopy of linearly conjugate molecule what Professor Datta has discussed in one of the modules of particle in a box. So what it is said that for a particle in a box to the pi electrons in butadiene, what is the structure of butadiene? Let me draw it. So butadiene, means four carbons are there. One, two, three, four, and diene. There are two double bonds are there. So this is butadiene, right? So in this butadiene system, when there are how many pi electrons are there? There are four pi electrons, right? Four pi electrons. So we can use particle in a box to understand the spectroscopic properties of this molecule, the HOMO-LUMO gap and this. Uh, Specifically, suppose four pi electrons are there. So what do you know that? So how many four pi electrons means these? So the first two are located in the so suppose if I think of a energy level of uh, a particle in a box, then the E1 and E2 will be occupied. So E2 will be our HOMO and E3 will be LUMO, lowest unoccupied. Right? In terms of that, we can get the HOMO-LUMO gap, right? Because now the gap will be the energy gap between E3 and E2, and we know for a particle in a box, the energy is given by n square h square by 8 ml square, where L would be the length of this uh, box, obviously, but here the box is a conjugated molecule. So we need to get the length of this molecule, right? So there comes an interesting thing why we are discussing this question. So first of all, see that what is the distance between. So this is the case for a butadiene, right? So using the similar argument, they want us to see that the length of hexatriene is given. That is, hexatriene is similarly, hexatriene means 1, 3, 4, 5. So trienes means and then so this is hexatriene. So we need to see that show that the fast electronic transition is predicted to occur at 2.8 into 10 to the power 4 centimeter inverse. Okay, so this is the structure of hexatriene. And earlier, what we have discussed is butadiene. And from here, what do you see? How many pi electrons are there? 6 pi electrons, right? Now, suppose if we are considering the similar particle in a box model, then what do you think about the energy levels? So, suppose this is my energy scale. These are the scales above. So, obviously, this is my ground state E1, right? Then E2, E3, E4, E5. Now, suppose for hexatriene we have 6 pi electrons, right? So, what do you think where the electrons will be located? So, what will be your HOMO? What do you think? What is the HOMO going to be? Highest occupied molecular orbitals. So, each of the energy levels will act as an orbit, right? What we were discussing earlier. So, E1 will consist of one pair of electron. E2 will consist one pair of electron. E3 will consist another pair of electrons. So that is total 6, right? So now you can see our HOMO is E3. Similarly, LUMO is E4. So the fast electronic transition is predicted to occur. So the electronic transition will be taken place between LUMO and HOMO, right? So the energy gap is E4 minus E3, that is suppose n so okay, this. I hope you are getting the idea what we are doing here. 4 square minus 3 square square by 8 ml square. So L is given also, right? L is 867 picometer. I have a statement regarding this, but let us first do the problem, solve the problem, and then I will discuss something about this. So see, so this is 4 square is 16 and 3 square is 9. So 16 minus 9 would be 7. 7h squared divided by 8 ml square, and we can put the values 6.626 minus 34 square of this joule square second square divided by 8 into 9.31, sorry, 9.11, 9.11 into 10 to the power minus 31 kilograms, and L square is picometer. So 867 into 10 to the power minus 12, right? We will, in terms of meter, this would be meter square of this one meter square. Okay. So, obviously we are doing in SI unit, so you can understand that. Uh, so let me do one thing. I will just break it down. One of the joules. Okay, so it is joule square. So I am taking one of the joule and break it down. As you know, joule is kg meter square second minus 2, right? So I have taken one of the joule and broken it down so that we can uh, play with cut these things, right? As you can see, only joule is going to be there, the unit in the numerator. So I am going to erase these things. Huh? Let me not erase so that, but you can understand that whatever answer we are going to get, it is in joules, right? Now, whatever the answer they wanted is in centimeter inverse. So how can we convert joule to centimeter inverse? So in spectroscopy, this is very means this has to be done regularly. So there is a technique. Suppose you know that energy differences, we know this is E is hcy lambda, right? Let me write delta E, that is most suitable, hcy lambda or h mu, right? So these specifically in SI unit it is joule. Huh? But you see, when we are expressing the energy in the centimeter inverse, then what we have to do, we need to, if we divide delta E by hc, so we are left with 1 by lambda, right? Then you can understand that it is going to come something like in meter inverse or so, right? So if we divided the delta E, suppose this is also delta E, right? So if we divided it by HC appropriately, so we can get centimeter inverse. How we will get, I will show you. So I am not calculating the whole thing now because I want to show you something. I think I have received a query. I will just write it and I will look for it. Just give me a second. Okay, and this is in joules till now. Okay, I'll just check what, I think there is a message. Checkbox. Okay, I'll do that. Question 9 of assignment 3. I'll do this after solution of it. Okay, I'll keep it. So, so what I'm going to do is that I'm going to divide this whole factor by HC. so that I will get the answer in terms of centimeter inverse. Okay. So if I so right now what I'm going to do delta V divided by HC. So that is I'm not writing the value of H because you can see I will going to cut one of the H with denominator with the numerator. And C, for C, I'm particularly writing in terms of um 3 into 10 to the power 10. That is centimeter, second minus 1. So I'm writing not in terms of meter, but centimeter. So that I am going to get centimeter inverse. Okay. And let me write down the value of each ones here so that you all are in the same page. 6.626 into 10 to the power minus 34 joule second. Right? The unit should be there. So this joule and joule will go second inverse one. So ultimately you see we are going to left with centimeter inverse, the unit. So I'm going to write my answer here. Before and this cut with this. So let me use my phone and give you the answer, whatever I'm going to get. Right. 7 into 6.626. So I'm getting something around 28,000 to 1.6 centimeter inverse, which is nothing but 2.82 into 10 to the power 4 we can write, right? So see, we are our predict means if we are predicting it to be similar with the system to be similar with etc in system to be similar with the particle in a box, then uh, the energy of transition of the first transition we are getting mathematically is 2.82 into 10 to the 4, which was predicted to occur at 2.8 into 10 to the 4. So this is almost same, right? So do you have any question till now regarding this numerical problem? Did you understand how we can uh, solve this kind of problem where the conjugated system will be given, the number of pi electrons is given. Sometimes it may not be given. So you need to see that how many pi bonds are there. See here, 3 pi bonds are there. So each pi bonds consists of 2 electrons. That is why 6 pi electrons. So uh, so may not. So only the system is given. Suppose hexa. So because it is a chemistry course, right? So it can be means the professor can think like that you know the structure. If the structure is given, maybe the structure will be given, not only the hexatriene name, but if the structure is given, will you be able to solve this kind of problem? For suppose something like if 8 pi electrons are there, something like that. Will you be are you confident enough to solve that?
Okay, no problem.
Yes. So one more thing I wanted to show you here, another discussion that see here it is given that the length is 867 picometer, but it may not be given everywhere. Okay. So what I'm trying to say, I will just write it here. Suppose this length etc. in So this is given that the length is 867 picometer. But it may not be given, then what you are going to do? Sometimes it is also given in terms of that CC double bond length is 134 picometer. C double bond length is 154 picometer. Okay. Sometimes it is given like that. Only this information is given. Only this information is given and your structure is given. Then how are you going to calculate this total length? It seems to be easy, but it is not. So let me show you how. Suppose there are three pi bonds are there, and how many single bonds? Two. So what one will expect that the bond length is going to be 3 into 134 plus 2 into 154 picometers. But when we will calculate it, let's see what is the value we are getting. We are getting only 710 picometer value. But see, the length is supposed to be 867. Can you tell me how can we do that?
because of delocalization.
Hmm. Because of
Because of
the
delocalization of resonance is there.
hmm.
So this is not exactly single bond and double bond. This is in between one point something bond order is.
Yes, if we think like that, then again my bond length is going to decrease, right? Because suppose if I think like that, all are something like the bond order is 1.5. Suppose this is what you are saying, suppose, right? So then my bond length is even going to decrease, right?
Another thing is the electrons are not arranged in a straight line here. The particle in the box,
Yes.
so we assume that it is the bond that is box length is the state
Hmm.
of L is equal to 0 to L is equal to 1 say.
Hmm.
But here all the bonds are not in the same line in the straight line.
Hmm.
There is some
Okay. So you are
effect of
close to.
surrounding.
So you are close, but let me give you another point of view. So whenever the bond length are given, bond distance are given, these are given from center to center. So uh, please bear with my poor artistic skills. So I am going to give you just the idea what I'm trying to say. So the bond length is often given from center to center. So suppose there is another atom is there, right? So these are carbon atoms, and think like that. These are all same, have same size, huh? Because all are carbons, right? Here. So just think like that. These are all same size. Uh, due to my artistic skills, let me try to draw it better. Mm, it will be better if I draw the spheres first. Like this. So while I'm drawing, can you guess what is the answer? So you are almost correct, means your points are correct, but something was missing. So this is your. So what I'm trying to say is that your electron doesn't only on to the bonds, but it will be delocalized all over the molecule, right? So when we are considering only the length from the bond length, then we are missing out two portions. So those are uh, okay. So that time we are neglecting this half of the half two times, right? We are neglecting, we are neglecting this part and this part. And if you think, if you see, if I add this, so how much will be this? So this is almost we are missing out one of the atom, right? Huh? So that diameter is almost close to 154. Huh? So suppose I am adding 154 with this. Now you see how much we are getting? 864. Can you see that it is close to 867 and almost that part what we are missing when we are considering the only the bond length.
Yes, yes, it is.
So when the bond length is not given directly, that and if the only the bond distance are given, then what you need to do that you need to obviously add up the bond lengths, how many double bond and single bonds are there, and with that just check. You can add one of the diameter of one of the uh, or one C single bond C bond. Okay, so that would be close to your uh, conjugated length or total delocalized total length where the electron can move around. Okay, so just a tip to you when these things are not given. So I thought I should share this thing. Anyway, I hope this is clear. Now suppose you are given so suppose let me go for octa tetraene. Maybe you can tell me that what is going to be the length, huh? There is no space at this side, so I am drawing. Huh? So four double bonds are there. So what is going to the length for this molecule? So obviously four double bonds plus one, two, three single bonds, and if we just left at that, we'll be wrong because half of this and half of that is left, right? So let us multiply, add up this, and this is going to be the whole length. I'm not right. I'm not calculating this. Just for another example, I'm giving this. Okay. Okay. So after solving the next problem, let me, as you have requested to solve the assignment 3, that problem, I'll just well, go to Google maybe, and we'll go to that question number 9. Um, I hope you can see my screen. I'll just sign in. So I have also enrolled myself as a learner in this course, so that I can also get the um, question number 9. Okay, question number 9 means you wanted to discuss this question, right? Can you see the question in the screen? This question. You are talking about this question, right? Question number 9, assignment 3.
Yes, yes, it is.
Okay. So the question says, consider a three-dimensional harmonic oscillator. Hamiltonian will be given like H cap, that is equals to px square by 2m plus py square by 2m plus pz square by 2m, where the p will be obviously is linear momentum operator, plus half m omega square in bracket parenthesis x square plus y square plus z square. The number of distinct eigenstate with the energy value 5 by 2 h cut omega is or are going to be what? The accepted answer is given as 3. So to proceed with this, so let me go to the PowerPoint. So where we can discuss this better. Let's take a blank slide here. So I'll write the things down. So three-dimensional harmonic oscillator, and the Hamiltonian is given p square by 2m, then p y square by 2m but plus p square by 2m plus half m omega square x square plus y square plus, sorry for that, plus z square, right? It is given, and it is also given if my expected or the average energy of my system is 5 by 2 h cut omega, then what is the degeneracy of the state, or how many state can have this energy, right? The degeneracy means what? Energetically degenerate. Means the states will have same energy value, right? So this is my operator. And for a harmonic oscillator, similar to the separation of variables what we have done for particle in a 3D box or 2D box, what we have learned so far. We have learned that the wave function is the total wave function will be product of wave functions from different dimension, right? Of x, y, z direction. And what about the total energy? Total energy is going to be a sum of ex plus ey plus ez, right? So this is the energy is going to be sum. Now, what is the expression for energy of a suppose only on one dimension for a simple harmonic oscillator? That we know is V plus half h cut omega, right? Where V can start from what are the quantum number possible? Can you tell me?
Uh, 1, 1, and 2.
No. The here actually for a particle in a box, the quantum number starts from 1, but the quantum number for a harmonic oscillator will start from 0 itself. 0, 1, 2. So what I'm trying to say that suppose it is in one dimension, then this is the energy expression, right? So in that case, what are the possible? I'm not going into the 5 by 2 case yet. I'm just describing the general energy expression, right? So suppose this is my Vx now, right? So in case of Ey, what it would have been? It would be Vy plus half h cut omega, where Vy could have been 0, 1, 2, 3, and positive integers. Then z, for z also it is similar, Vz plus half h cut omega, right? Now see my total energy, or energy of the three-dimensional SHO is given 5 by 2 h cut omega, right? So let me add them all up. So if I write it like Vx plus, suppose right now I'm summing them up, right? Plus 3 by 2, right? Please let me know if in any step you don't understand, please tell me. So suppose this is my equation A, this is my equation B, and this is my equation C. So if I am adding up A plus B plus C to get total E total, right? So this is going to be total energy. And see what we are getting this step. We are getting the H cut omega can be cut. So we can cut H cut omega. This is one. What we are left with? We are left with Vx plus Vy plus Vz plus 3 by 2 is 5 by 2, or we can also say we can take 3 by 2 this side as a negative, and we will be left with 1, right? So now we have to look back that what are the possible values, what are the values of Vx could have been, so that my total Vx plus Vy plus Vz would be 1, and only in this condition my total energy is going to be 5 by 2 h cut omega. Is this making sense?
Yes, yes. So
So,
Vx plus Vy plus Vz is equal to 1. That means 0, 0, and another one is 1.
so this is one state. So one state could be 0, 0, 1, right? So suppose I am writing it x, y, z over here. Huh? So one could be 0. So Vx, Vy, Vz, right? Let me write it. One would be 0, 0, 1. So are there any possible, what do you think about, are there any degenerate eigenstates? What could be the other?
Yes, three degeneracy.
Huh?
Vx is 1, others are 0, and Vy is 1, others are 0. So
Right.
we get
So we are going to get
degeneration 3.
three degenerate states, right? So that is what was one. So if so for so the if the question is framed in the similar manner but given with a different total energy, then obviously I hope you will be able to solve the problem, right? So the question was like this, and the total number of distinct eigenstate with energy value 5 by 2 h cut omega is going to be, there will be three states, and we have also shown you that what are those states are going to be, right? Means obviously you can write down the wave functions. Like the wave functions will be again be a product of psi 0 into means the product of three different dimensions, right? So we are not going into that, but the degeneracy is three that you would be able to do it. Suppose the question says 7 by 2 total energy. Then what will happen if it is going to be 7 by 2? Means I'm just thinking differently. I mean, another number, just I'm not sure that, obviously that is going to be degenerate. I'm not sure. After doing that, we will be know. So in that case, your suppose, so the question I was saying that suppose your Vx plus Vy plus Vz is going to be 2. Because what I'm saying is this 7 by 2, 7 by 2 minus 3 by 2 would be 2. Say, then what are the possible states?
0, 1, and 1.
0, 1, 1, 0, 1, 1, 1, 0, 1, right? 1, 1, 0. Is 0, 0, 2 is also going to be another option, right? 0, 2, 0, 2, 0, 0, right? So in that case, you are going to get 6 degenerate states. You're getting my point.
Yes.
So I hope you will be able to solve further. So suppose your Vx, Vy, Vz is equal to 3. Then by unitary method, you can obviously see you are going to get 9 degenerate states, right? Because whatever was 0, 1, 1 now will become 1, 1, 1. Oh, if it is become 1, 1, 1, then this is only one state, right? So it's not so. My question was, I guess, confusing. Suppose Vx plus Vy plus Vz is becoming 3, then how many degenerate state would be there? It would have been 0, 0, 3, 3, 0, 0,
6 degeneracies.
0, 1, 1, 1. Right? This would be one option. What would be the other option? 0, 2, 1, 2, 1, 0. Oh, there could be multiple actually. 1, 2, 0, then 0, 1, 2, then 0, 2, 1, 0, 1, 2, 2, 1, 0, 1, 2, 0. Suppose, and then here would have been um, what else it could have been? You start from 1, 0, 2, right? And did I write 2, 0, 1 here? No. And are there going to be more steps? So see, right now it is not 9 only, there are 10, 10 degenerate states, right? If Vx plus Vy plus Vz is equals to 3, I have to look if there are more possibilities with 0, 2, 1 with each other. So there are three numbers, three different numbers, 0, 1, and 2. So it's all that permutation and combination, how many we are getting. I think we can get some more. I'm not sure. That is a question for another time. But I guess you got the gist what we are trying to discuss, right? So we can get back to the our usual questions, right? May I?
Okay, sir.
Yes. So as we were discussing particular harmonic oscillator, so let us actually solve one or two harmonic oscillator problems, and then again we can go back to uh, the usual particle in a box problems, right? So, so these questions are also from Macquarie. Macquarie is physical chemistry. So see, the question state the first question that the molecule is H79Br, HBr, right? So where the atomic, so the H, bromine, uh, the isotope is 79 bromine, and it is said that there is an intense line at 2630 centimeter inverse. So infrared spectrum line. So that means it is related to vibrational spectroscopy, right? Oh, sorry, that. So for vibrational spectroscopy, uh, you know that what is going to be the uh, uh, what are the relationship we know. With one of that, we are going to solve this problem. So let us read the question another time. So in the infrared spectrum of H79Br, there is an intense line at 22,630 centimeter inverse. We need to calculate the force constant of the molecule and period of vibration of the molecule. The force constant. Do you remember? So I'm going to write down a few formula. So you need to tell me that which formula we are going to use here. So one is force is equal to minus kx, where our k is force constant, right? And x is obviously displacement from equilibrium position. You can say. Another formula is uh, your omega is, oh, not 1 by 2 pi. Let me write it. K by m, where m is mostly reduced mass, because here we are working with a two body problem, right? HBr. Huh? So obviously the mass of bromine is and size of bromine is very high, right? Than the H. So the mass is also different. So what we are going to do is that we can rotate, we can convert this M1 and M2 in terms of a reduced mass, that is mostly given by mu 1 by M1 plus 1 by M2. Another way to write is, so I will change my notations here a little. So K by mu, you already know what is K, right? And omega is actually angular frequency, right? So this we know, angular frequency. Now there is a relationship between angular frequency and a normal frequency. So that is actually omega is equal to 2 pi mu. Okay. So if I put that here, so your frequency mu is going to be 1 by 2 pi k by mu. So see, we are going to use this formula here. Huh? So obviously this is in frequency, so we need to convert it. So we need period of vibration. Period of vibration is 1 by nu. That is the time period, right? Period of vibration, that is going to be 1 by tau, right? 1 by nu. So what that would have been 2 pi mu by k, right? But to get that, we need the value of force constant, right? So for that also we have another formula. See, frequency is here. How frequency is related to wave number? See, I always remember it like by that. That delta E is hc by lambda and also h mu, right? So we can always relate it by this. That frequency is velocity of light by lambda, and 1 by lambda is your wave number. Okay, so your wave number mu bar is going to be 1 by 2 pi c. C is the velocity of light, k by mu. Now you see what are the things given. Your in infrared spectrum intense light at 2C30 centimeter inverse, that is your wave number. So that is given. You know the value of pi, you know the value of speed of light in vacuum, you know what is reduced mass. Why? Because the HBr is given and what is the isotope is there, that is also given. So you need to calculate that. So we will get mu reduced mass also. So the only thing we don't know, that is going to be my force constant. So we'll be able to do that. Suppose the formula would be 4 pi square c square nu bar square into mu, right? If I remove the square root, if I square both the sides, then I am going to get some equation like this. And this is my force constant K. We know all these values, so we'll be able to calculate the force constant. See, this is a problem related to the harmonic oscillator only, huh? Simple harmonic oscillator. And if we can get the value of force constant, then we'll be able to. So for the period vibration, we will not go that far. We can also calculate it from here. So, but do you get it till now? Is there any confusion at this moment, at up to this point?
If we put the value of force constant K in the formula of nu bar is equal to 1 by 2 pi c root over K by mu, we get
Hmm.
the same thing on both sides, left hand side and right hand side. How
Yes.
we come to get the result?
No, no, I'm not saying that. Suppose I'm saying, you tell me one more time what you said.
If we put the value of the formula of force constant into
Hmm.
the nu bar is equal to 1 by 2 pi c
Huh.
square root of mm, force constant by reduced mass.
Right.
Then the
No, no, I'm not saying we will put this thing into that. I am saying that we are getting this from here. So,
yes, yes,
so what I'm trying to say
yes,
is that from here we can write the force constant is equals to this, and these are the known parameters. So that way we can calculate the force constant. So let us do this for the first question, right? So we have a blank page here. Maybe we have, yes, we have one. So the force constant K is 4 pi square. Uh, this inverse square, right? What else was there? C square and reduced mass. But before that, let us calculate the reduced mass. Reduced mass is M1. Sorry about that. Reduced mass is M1 M2 divided by M1 plus M2. Here M1 is 1 AMU, means for suppose for hydrogen, and bromine is suppose M2, that is 79 is given, right? Bromine. So how much our mu is going to be? 1 into 79 is going to be 79, and denominator it would be 80 AMU. Now we need to convert it into kg, right? So that would be 79 by 80 into 1.66 into 10 to the power minus 27 kilograms. That is how we convert atomic mass unit to kilogram. We have done nothing, I guess. Uh, uh, if you think like that, this is a mass of one atom. Now, if you divided it by, I guess, if you divide it by the Avogadro number, then I guess that is the same thing. Just let me check if I am stating the correct thing. Yes. If you divided it by the Avogadro number, then you are going to get in grams, and then suppose AMU, if you divided it by the Avogadro number, then you are going to get it in grams, and then from grams you can go to kg by again divided it by 10 to the power 3, right? So anyway, so for atomic mass unit to kg, this is the conversion formula. So let us put these values here. So 4 into pi square is 3.14 square. This is given 2630. But remember, this is given in centimeter inverse. So square of that will become centimeter minus 2. Then c square. So 3 into, now c. I would be happy if we can cut the unit centimeter minus 2, right? So So I will have it in 10 to the power 10, so that I can, instead of meter, I will go to centimeter, and the square of that would be centimeter square second minus 2, right? And just let me make a wall between these things so that these two are separate calculations. right? This is the, so I have done this, and now the reduced mass I will add. So 79 divided by 80 into 1.66 into 10 to the power minus 27 kilograms. Now see what we are going to get. So, so these centimeter minus 2 and centimeter, this is gone, right? And let us calculate the value by calculator, and I will tell you what is the value we are getting. 4 into 3.14 whole square multiply by 2630 square of that multiplied by 3 into 10 to the power 10 square of that multiplied by 79 divided by 80 multiply by 1.66 multiply by 10 to the power minus 24. Oh, not 24, 27. And that is leading to a value of 402.45 kilogram second minus. Okay. Now let's see if we have done it correct. The unit is correct or not. How can we do that? Remember, I have given you a formula that force is equal to minus kx, right? Where k is force constant, ax is displacement. We know what is the unit of Newton, right? What is Newton? Again, kg. Force is mass into acceleration, kg meter second minus 2, right? And what is x? That is meter. See, meter and meter will cut. So you can see the unit of force constant is going to be kilogram second minus -2. So we are correct. So I am erasing this. I was just cross checking, and this is a good way to check the units are correct or not. So the force constant is obtained. Okay. Now what was the second part of the question? That period of vibration. So the period of vibration, uh, we can actually see that we have this equation in hand, right? That C nu bar is frequency. So tau is 1 by nu, then it is going to be 1 by C nu bar. So C is 3 into 10 to the power 10 centimeter second inverse, right? Multiplied by 2630 centimeter inverse. So centimeter inverse, centimeter is gone. See, second inverse is coming above as a unit because it is unit of time, right? And 1 divided by, so we are getting somewhere around 1.267 into 10 to the power minus 14 seconds. So this is my period of vibration. Means one vibration is taken place in this time scale, right? So this is my second part of the, and this is my first part. So if the molecule is given, if you know the reduced mass, then And if you are given with the wave number, or you can say that oscillation frequency, then you will be able to calculate the force constant, right? So that is the first question. What the second question is about, that the force constant, another molecule. Now this is bromine. 79 bromine, 79 bromine. Another way to write is 79 bromine to Br2, right? Now see, the force constant unit, another way to write is Newton meter inverse, right? Let's see, we can, if we can write it like that. So 402.45, if we multiply, suppose kg meter second minus 2. So I have just multiplied meter here, so I need to remove that also. Now see, this part is Newton and this part is meter inverse. So another way to write the units is Newton meter inverse. Okay. Okay. So similarly, so the question states that the force constant of 79 bromine and 79 bromine is 240 Newton meter inverse. Calculate the fundamental vibrational frequency and the 0 point energy. Okay. So now fundamental vibrational frequency. So that is my new bar or new, right? So I just have to do the reverse thing. Okay. So my new was 1 by 2 pi k by mu. So my mu is now 79 into 79. Then below it is 79 plus 79 AMU. So I can take 79 common actually, so it would be good. It would be something like this, right? So 79 by 2 AMU, and I'll put it directly here. 1 by 2 into 3.14. Inside the row, value of K is given, that is 240 Newton meter inverse. So another way to write it, Newton meter inverse is kg this, right? Kg second to the power minus 2. Why I have written it like that? Because I know that I will need the thing in kg. Kg, and right. So my kg and kg I can cut, and second inverse is, so second minus 2 is in the root. So outside the root my unit is going to be second inverse, and that is also known as hertz, right? So that is obviously my unit of frequency. So I will just calculate it using my phone and check what is the value. 1 divided by 2 into 3.14 multiplied by, so let me do it. So 240 divided by 79. I think am I making any mistake somewhere? 29. I am actually getting a very big number. In terms of frequency, let me write it down, and you will see that 96330592876, and then point something. Obviously, we I could have write it in terms of 9.6 into some to the power 10 to the power something, but in calculator it is not coming like that. So what I will do is, suppose if I now try to write the frequency in terms of wave number, then it will be my nu by c, that is the speed of light, right? I'll just do that. I will just divide it by 3 into 10 to the power 10. So that time I'm getting something around 321.12, but now my unit would be centimeter inverse. So that's why the frequency, frequency, so this way, so we know we have got something in terms of wave number, right? The centimeter inverse. But in the question, it can be like frequency is 321 centimeter inverse. So you need to understand that new bar is given, not the new is given. Are you getting my point? What I'm trying to say here. So, so the
Yes.
interconversion between this unit, you have to know this. So then the rest of the things will fall into the place. I'm just worrying that if the value is what we have obtained, 321, or the previous value is correct or not, I'll just do the calculation once more so that we are not making any mistake. So 1 by 2 pi into root over 240 divided by mu. So let us solve the root first. 240 divided by 39.5. Yes, actually what we have done is correct. So these are the two ways to represent the answer. Now we have got the fundamental frequency in terms of this. What is the next part? The 0 point energy. Obviously, we know the formula of 0 point energy, that is E0, right? That is 0 plus half h cut omega, right? So another, so this is half h cut omega. How we can write it? See, half. This is h by 2 pi, right? And also we have learned that this is new. This uh, this is 2 pi new, right? So this is in terms only h new. right? So another way would be H C nu bar, right? So let me write the value 1 by 2 into 6.626 into 10 to the power minus 34 joules second. Now 3 into 10 to the power 10 centimeter second inverse multiplied by 321.12 centimeter inverse. Centimeter inverse, centimeter will go. Second inverse, second will go. Now energy will be getting in terms of joules only. 321 point this multiplied by 3 into 10 to the power 10 multiplied by 6.626 into 10 to the power minus 34 divided by. So we are getting something around 3.19 into 10 to the power minus 21 joules. So this is the value we are getting as a 0 point energy. So these kind of numerical problems also can come from the harmonic oscillators. Okay. So is this clear till now? So let us change the test again and let us go
Yes.
to some questions from numerical question from particle in a box maybe. So that would be good actually if we can hop around between two, then our uh, uh, we can that would be actually good. So suppose this is another question from another question. So the question states that so many protein contains metal porphyrin molecules. The general structure of porphyrin molecule is given. So so this is a actually the whatever the picture structure is given. This is a general structure of porphyrin molecules, right? So see there are four nitrogen heteroatoms are there. So this is something like a cage molecule. And what are the informations are given? That this molecule is planar, and so we can approximate the pi electrons as being confined inside a square. So they are trying to say that think of it as a particle in a 2D box. Okay, so they are trying to say it like that. Why? Because the molecule is planar. Now, planar and they are in a confined state, obviously. So that's why. So, like that. Now, they are asking that what are the energy levels and degeneracies of a particle in a square of side A, where both Lx and Ly are same square. Now, there so as there is some symmetry in the molecule, then there would be some degeneracies as well as Professor Datta has discussed that symmetry and degeneracy go hand in hand, right? So we expect there would be some degenerate states will be there. What what are the other information that is given? It is given that the porphyrin molecule has 18 pi electrons. Now see, there is an actually a contradicting statement. So these porphyrin, they are actually have 26. If you see how many are there, let us see, huh? How many bonds are there? One, two, three, four, 5, 6, 7, 8, 9, 10, 11. Right? 11 into 2, 22, and there are this the lone pair electrons are there. Have I said it correctly? Let me see. So 22 from here, and there are, I guess, 1, 2, 3, 4, 5, 6, 7, 8. So that many total number of electrons are there. But why they have stated that this has a 18 pi electrons? Actually, they have missed one information that actually these 18 electrons are from one plane. Rest of the electrons are not in the plane. So I will show you the plane what they are saying. I will erase this part. I will color it in red. So you will understand that which pi electrons or what plane they are talking about. I'll just so the red line I am drawing around the structure, that is actually the plane containing the pi electrons. Other pi electrons are there, but the 18 pi electrons they have mentioned are in this plane, and that is the only the that is planar. Rest of is not. So you see right now. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. So 9 twos are 18. So those are 18 pi electrons on that plane. Okay. So we need to concern with that 18 pi electrons. Then the next statement what they have given is that if we approximate the length of the molecule by 1000 picometer. So this one side, what they are saying that this one side is 1000 picometers. Obviously, if it is a square, then this is also 1000 picometers. Right? X and Y are same. Then what is the predicted lowest energy absorption of porphyrin molecule? See, earlier whatever we are doing are a single chain or those kind of molecule, we are predicting it to be similar with uh, particle on a particle on in a box problem. Means particle in a box, not means it is was in a one-dimensional problem, 1D box. Now it is 2D box, right? Because it is something like porphyrin molecule, it is not linear, it is something like a square shape. So we have to consider it a 2D box. So let us remind ourselves what is the energy formula. It is energy of Enx plus Eny, and if it is a square, then we can write it quite nicely. Nx square plus ny square, h square, 8 m L square. L is 1000 picometer is given, right? So this is my formula of energy. Now let me see what are my states are here. See, it is 2D box, right? So there is some it is a square. So there are some degeneracies that we expect. So I'll just write down that what are the degeneracies would be, degenerate states. So obviously there are 18 pi electrons. So let me write down the Actually, let me draw the energy state first. So, suppose this is my energy scale. Energy goes increase from down to up. So obviously my first state would be 1 comma 1, right? So what is going to be, suppose, so these are my variables, right? So let me take this thing as constant, h square by 8 square, huh? So can I say that it is nx square plus ny square beta? So I am defining beta as h square by 8 square so that we can write the energies quickly. So the energy would be 2 beta for this state. Now let us think about these two states. One is 1 comma 2, another is 2 comma 1, right? What are the energies going to be? 5 beta. What about the next state? The next state, it is going to be 2 comma 2, right? So it is 8 beta. What is the next state going to be? It is going to be 3 1 1 3, right? So 9 plus 1, that is 10 beta. The energy gap is not to the scale. Okay, I'm just writing it. 3 1. What would be the next? 3 2. 3 2 and 2 3. Both will be degenerated. So 3 square is a 9 and 2 square will be 3. 9 plus 4 is 13 beta. What is going to be the next? 3 3. 3 3 energy is, suppose 3 3. Then what is going to be the energy? 9 plus 9 is 18b. So I hope you understand why I kept one gap, because this is actually 4 comma 1 is going to get here, because see 4 square plus 1 square, see 17 beta is going to be in between those two. Obviously, and there are, let us fill the electrons also, huh? We have 18 pi electrons, right? So each can have two. So let us fill that also so that we can get the idea about the HOMO and LUMO, right? How many states we have filled? 1, 2, 3, 4, 5, 6, 7, 8, and 9. See, they are degenerate. They we so we cannot fill one state, right? According to the Hund's rule, we need to fill first fill them with the unpaired electrons, and then we can fill them, right? So these are 18 pi electrons are there, and these are my states. So my HOMO is a degenerate state here, and LUMO is 13b beta. Are you getting my point? What I'm trying to say here?
Yes, sir. Okay.
Okay. So now uh, the gap is obviously beta. So the transition can possible is 1 comma 4 to 3 comma 3, or 4 comma 1 to 3 comma 3. So the gap is beta delta E beta, and that is sorry, that is h square by 8 ml square, right? Now one can plug in the value of this, and L we have approximated it is 1000 picometer. Picometer means 10 to the power 12 meter. Square of that, meter square. So we will get some values in joules, and then we obviously can convert into centimeter inverse. That we have learned. But here from this question, what we have learned is that how. So the previous question we solved this for a particle in 1D box. Same thing. How to get the homolumo gap. Here we are doing it for the a molecule in a plane such that something it is forming, it is actually related to the particle in a 2D box. See, the way of solving is same, just the the states now are degenerate. So these are the things we need to keep in mind. Okay, let us we can solve another question maybe. This is very easy question. The question is asking that what are the units, if any, for the wave function of a particle in a one-dimensional box. So the question wants to know the question is what is the unit of the wave function in a particle in a box. So for that, I am giving you one-dimensional box. So I am giving you the wave function. And this is the wave function. Can you tell me what is the unit of the wave function? Does it have a unit?
Yes, sir. This is centimeter inverse.
Mm, not inverse, there is square also, square root also. Actually, if I am talking out in meters, then it is meter to the power minus half. Right? Because it is 1 by root over L. Right? It is 1 by root over L. So it is meter to the power minus half is the unit.
Sine of x by L, it is unitless.
That is unitless
The
because
sine
this is a
function is
trigonometric
unitless.
function, right? That is unitless, but you have unit on this side, that root over 2 by L, because L has meter, right? So it is meter to the power 1 by 2 because there is a root. If the root was not there, then it would have been meter inverse. But as the root is there, so the unit will be meter to the power minus half.
The unit do not make any sense.
It doesn't make any sense to be honest. But just to give you an idea that,
Okay.
right. So okay, so let us we have another question actually with this. Uh, Let us solve this question. This is also a quite good question. I will just delete. I'll delete the previous part, or maybe if I can, if I can, yeah, that will be good to remove it. this side, so it will not overlap with the previous after. So the question says that prove that the set of functions, the psi nx, is given as, so you may not be able to see it properly. I will write it here. Psi nx is 2a to the power half e to the power I pi nx by a. This is given, where n can be 0 plus minus 1 plus minus 2. Okay, so we need to prove that this is an orthonormal function over an interval minus a less than equals to x less than equals to a. Okay, we need to prove that this is an orthonormal function. How one will do that? I'll write it again here. Psi is, I will try to write it in a better format so that it will be helpful. 1 by 2a root over 1 by 2a exponential I pi nx psi n I pi nx by a. Okay, so this is your function. So we need to prove that it is an orthonormal function. That means, and in a this area minus a to a psi n star psi n d tau, or suppose this is a one dimensional problem, so dx is 1. If I prove this, then I will prove this is normalized, right? And if I can prove that, suppose instead of n I have something such as m, psi m star psi n dx, if I prove this is equals to 0, then I can prove this is an orthogonal function as well. So both, if I can prove that they are following both the things, then I can say they are orthonormal. Okay, so let us do one by one. Let us see if it is a normalized function or not. To do that, first we need to take the complex conjugate of this, right? So the constant, there will be no change, but the exponential, there is going to be a change, e to the power minus I pi nx by a, right? Because that has an imaginary part. So in the complex conjugate, it is going to be minus. So let us do the integration minus a to a psi n star psi n dx is equal to minus a to a. Obviously outside the root, now I am going to have 1 by 2a, and inside the root I have e to the power I minus I pi nx by a multiplied by e to the power I pi nx by a dx. So I am multiplying two exponential function, so I can add the order, right? What I meant by that is, it is something like I pi nx by a plus I pi nx by a, right? And you will see this is 0, right? Eventually, what I got is 1 by 2a integration of minus a to a e to the power 0 dx. E to the power 0 is 1. So ultimately, I am going to get minus a to a dx. And that is very easy, right? X a to minus a. So that is 1 by 2a minus minus a, right? So that is 2a by 2a, that is 1. So what I got is that minus a to a psi n star psi n dx is 1, right? So this condition tells us that this is normalized, right? Normalized. What do you think if I have done with psi m star psi m dx? I would have also got 1, right? Okay. Now we have to prove this is orthogonal. I will need some blank space, blank slides maybe. Let me arrange that. Might require two. So now we are going to see that what minus a to a integration minus a to a psi m star psi n dx is going to be. Obviously, my psi m is as a first term. Let me write what my psi n is. Psi n is 1 by 2a exponential I pi nx by a. So obviously my psi m is going to be, so these are just constants, right? N and m. So this is I pi mx by a. Okay. Acha. I am in the correct. What about then psi m star? So that is going to be root over 1 by 2a exponential minus I pi mx by a, right? So here we are going to get, are you following?
Yes.
Then 1 by 2a equal So this is minus, sorry, I forgot the minus sign. And n will be as it is, I pi nx by a dx. What do we have it here then? The product minus a by a. I will take 1 by 2a outside, obviously. And inside the exponential, I have I pi x by a and n minus m, something like this, exponential function. Okay. Okay. Now there would be one can try uh, multiple kind of process to solve this. So there is what I am going to do is a little bit different because what I have, so before solving here, I was trying to solve it by the normal thing, right? If we have an exponential function, what what would be the integration of that? I was doing it like that, and what I felt is that I am doing it for pages and pages, and it was not ending. So that's when I remember that we can do it by another way. So that is, if you remember the Euler's theorem, it talks about that if we something have e to the power I n theta, so that is actually your cos n theta plus I sin n theta. So I am going to use this to quickly solve this. So 1 by 2a in between integration, the exponential, this part, see, x is our variable, right? So x is like theta here. The rest of the part is not. So it is cos, or n theta is pi n minus m divided by a x. This is one cos. Then plus I multiplied by sine. So let me give another bracket. Let us use maybe the second bracket. Pi n minus m a dx. So 1 by 2a minus a to a. Oh, so no need to keep it. So we can directly get the integration, right? So what is the integration of cos function? So it would be something like cos theta is sine theta. So what I am trying to say, integration of cos n theta d theta is 1 by n sine theta, sine n theta. So similarly, it would be a by pi n minus m sine n minus m pi by a. Achha, x should have been inside this, right? And what is the integration of sine? That is minus. Minus sign will come up, and similar a by pi by n minus m will go here. Then integration of sine is cos, minus cos to be specific, pi n minus m x divided by a. So that is our integration is done, but the limits are from minus a to a. So I'll put them. So before putting them, we can see we can take a common from there and cut it with this, and also we can take one this n minus m, that thing outside common. So inside that now we'll put the value sine n minus m pi, because x, if x is a, then a and a are going to cut. So I will be left with sine n minus m pi. What about this part? So cos, similarly I will be left with cos n minus m pi, right? Then minus, now minus a I am going to incorporate, sine minus sine n minus m. So minus will be there, minus n minus m pi, and then minus cos minus n minus m pi. My bracket is closed. Let me see what I have. 1 by 2 pi n minus m. Now inside square I have sine n minus m pi minus cos n minus m pi. Now when there is a negative thing inside the sign, we can take it outside and the negative sign can come outside. So it will be sine n minus m pi. The cos, it will not come, right? Cos we can write as it is. Okay. Now see, we had that n or m would be 0, plus minus 1, plus minus 2. See, we had these conditions here. Okay. So if n and m are only going to be integers like this, then I can expect my n minus m, I should write it in a different box made somewhere. So what I'm trying to say is, if my n and m are all integers, then I can expect that n minus m is also going to be a integer. It could be negative or positive, but it will be an integer. It will not be a half integer, right? So in that case, my sine n minus m is always n minus m pi, right? So it's like sine pi, sine 2 pi, sine 3 pi. This is always going to be 0. So let us make it 0. So this is 0. This is going to be 0. I have made one mistake, is that this is sine minus cos, now minus, and this should have been minus minus plus. The minus sign is inside, but this I have mistakenly written, because I guess you can understand. Sine n minus m pi minus cos. Now when I'm putting the value of minus a, so now it is minus sine plus cos. Then we have put the value of minus a in place of x. So that's why this minus sign has come. But inside the cos, if there is a negative sign, that doesn't mean anything. That is same as the plus. Okay. Now see that minus cos n minus m pi and plus cos n minus m pi. If you think that, so if that is a integer, then they are not zero. That cos n minus m pi is not zero, but there is a negative sign before this and positive sign before this, and both the terms are same. So now they can be cut down. So overall, I got 0. Means whatever I am doing, minus a to a psi m star multiplied by psi m dx is 0. What does this mean? This means this is an orthogonal set also, orthogonal function. So earlier we have proved it is normalized. Now we are proving it as orthogonal. So psi n is equal to 1 by root 2a exponential I n pi x by a is is an orthonormal function in minus a less than equals to x in this range. Huh? That is what we have proved. And another way to write is minus a to a plus a psi m star psi n. Sorry, I have made a mistake here. It should have been n, right? Two different function psi n dx. It could have been written another term is Kronecker delta mn. This is another way to write. What does the Kronecker delta mean? This delta mn is 0 when m not equals to n, right? That's what happened when m equals to n. This is orthogonal that we have proved. And when it is equals to 1, when m and n are equal, that time it is following the normalized condition. So this is another way to write this. Is there any doubt in this question? Solving this. So I know you didn't have an earlier idea that what kind of questions we are going to discuss today, but still, I hope uh, you got the gist that what we have done. We have solved some numerical questions from particle in a box and harmonic oscillator as well as. Most importantly, we have done this kind of calculation, orthogonal and normalized thing where so this kind of problem can be solved for any wave functions, right? Not only for particle in a box. So it is not written for a particle in a box. You know the wave function looks like a particle in a box function. That's why uh, that is another thing. But the way we have done it is a general way to do it. So right now it's almost 9. So we have to stop it. I had a few more questions here. which we can look on the next session maybe. But I will keep these uh, uh, questions in the notes so that you can go through the questions when you are free maybe, so that the next day we can discuss these questions, right? So I think I had three questions like this, one, two, and these three question here, and another fourth question is remained at the end, I guess, here. So I will be very happy if you can try out this question yourself, and that would make our interactive session more interactive on the next day maybe. So as you can see, this question is show explicitly for a harmonic oscillator that psi naught x is going to orthogonal to psi 1x, psi 2x, psi 3x, and that psi 1x is orthogonal to psi 1 to psi 2x, psi 3x. The I have just solved the problem similar to that, right? You just need to add something more. Huh? So you need to multiply the functions and check the integration if you are getting 0 or 1. Depending on that, it will be orthogonal or normal, right? And the general a standard integration integral is solved on the right hand side, right? That formula is given for your benefit, so you can use that. But remember, for a harmonic oscillator, your range is from minus a to plus a. Here the integral is given, sorry, minus infinity to plus infinity. Here your range is given from 0 to infinity. So you may have to tweak your integrand in such a way that you can break it down from 0 to infinity. I will give you a hint here. The hint is that look if your integrand is odd function or even function. Okay. If it is a even function, let me write it down for you. 0. So minus infinity. Suppose it is minus infinity to plus infinity. Some integrand is there, I dx. Okay. If I is even function, then you can write it in terms of 0 to infinity 2 into this I dx. Okay, that you can do. But if I is odd, then this is actually going to be 0. We will discuss this in detail the next day, the next session, but try to solve it for yourself. Huh? So with that, today I'll be stopping. This thing will be there in the notes so that you can get idea, right? I will just maybe I will keep the questions which we did not solve today together so that the next day, means suppose the last four questions to be your homework, something like that, so that we can do it. Obviously, we will discuss about rigid rotor and all, but solving these problems are more important. Okay, so with that, let us stop today's session. I hope the session was beneficial for you. Let me unshare my screen. So with that, let us stop today. I hope you will be joining on the next session. We'll be meeting you, and this was beneficial for you. I hope so. Thank you for
Okay,
joining.
thank you, sir.
No need to call me sir. I am your junior. Please. Um,
Okay, okay, thank you, thank you.
yes, yes. We'll see you. Thank you for joining.